Hey everybody. So clearly that intro hopefully gave you a sense that we are jumping into an exploration of stats and probability, statistics and probability, and it'll last probably the next 2 weeks or so, and we'll have many different facets to it, including videos, um, uh, questionnaires by way of Google Forms, and probably some connections to Delta Math and even possibly Khan Academy. So let's get started by really answering the most important question, why do this? Well, you saw in the preamble there that we, of course, want to prepare you for the SATs, APs, MCAS, pretty much every STEM college course you'll ever take. But I think it's much more important to kind of think about it as we live in a very, very data-rich world now more than ever, and how do we make sense of some of this data that surrounds us? Here you're looking at a Forbes article from 2018. How much data would we create every day? And it's pretty insane. We're just going to take a look at the first paragraph. The amount of data we produce every day is truly mind-boggling. There are 2.5 quintillion bytes of data created each day at our current pace. But that pace is only accelerating. Well, I don't expect you to know what 2.5 quintillion bytes of data means. How about this next sentence, though? Over the last 2 years alone, remember this is written in 2018, 90% of the data in the world was generated. So data is being created at an enormous pace, and with the internet and with the ability to store that data, more and more of it is created. Much of it is garbage data, random kind of social media posts that people are creating or pictures that people upload, but much of it is also valid business data, science data that we can make use of and use. Here's another kind of thing to think about. A lot of that data is used for kind of insidious, or I don't want to use the word evil, but perhaps purposes that are not the best intentions. So the New York Times did um, kind of a multi-part series here called One Nation Tracked. This particular article talks about how a smartphone, your smartphone, is essentially spying on you, and you have some control over it, but not a whole lot. What I mean by that is this: your smartphone is probably sending your precise location to companies right now. Their job is to turn your shopping trip or doctor's visit into what we call big data, another term for corporate intelligence. So lots of it happens. Google Maps itself and Facebook are two of the biggest kind of players in this game, but they are unlikely to be selling much of the data, although Facebook this past year several times was found guilty of doing so. But what's much more likely to be happening is that they're collecting data about us that kind of gives them insights into our habits, our shopping habits, how we spend our time. And this is really kind of, even in the article, referred to as the Wild West, where it's unclear what they're doing with this data and it's unclear what's happening to our privacy. Think of a world where your medical information, that's data. Imagine if your medical information were to be accessed by parties who shouldn't have access to it. And suddenly you're unable to get insured because they realize you have pre-existing conditions or you have something genetic that has been passed down through generations. So there are many, many instances where we would not want our data to be out there in the world and for people to access it. In other instances, big data is very useful. So again, the New York Times did a multi-part series on climate change, and it has done this over the years. But this particular one I thought was relevant because when we have these so-called debates about climate change, it's somewhat silly because there is really kind of comprehensive, exhaustive evidence that climate change is real. And the question is, well, how do scientists know that there is in fact climate change that is man-made? And I would refer you to this kind of data here. So, for instance, annual temperature reports of multiple locations in the world, someone or some machine taking daily temperatures, where we can compare temperatures today or in 2019 here to those, almost 80 years ago or even further than that. If we want to go back farther than humans kind of recording temperatures, we can do it using, again, data. So let me just read this paragraph to you. In much the same way that data on the daily consumption of chicken wings can help us suss out the dates of Super Bowl Sundays, think about that for a minute. When Super Bowl Sunday happens, the consumption of chicken wings really goes through the roof here in the U.S. So if you, let's say, had forgotten the date of the Super Bowl, let's say it's 100 years from now and the Super Bowl no longer happens, and we wanted to go back and perhaps investigate when the Super Bowl and what day of the year it was happening. One way to do so would be to look at the sales of chicken wings. They would likely correlate with the highest sale of chicken wings is happening on Super Bowl Sunday. From a science perspective, we can take ice core samples, tree rings, look at corals, pollen, and cave deposits to see how the climate behaved in the past. So this particular professor calls it environmental forensics. So just a quick example here, for instance. Some tree species can live for thousands of years. When cut into, their rings, which resemble a bullseye on a tree stump, can clue researchers into not only past temperatures, but also moisture levels from year to year, and that depends on thickness of those tree rings. So what's obvious is that there's tons of data around us. We want to have some tools, some language uh, to describe that data and to make sense of it. So here's our premise. Last year, when we were in school, I asked one of my classes the following question. The question was, how many hours of screen time are you experiencing per day? And I'm chuckling because the results that I got last year would be almost completely unrecognizable to you this year, given how much screen time all of us are now experiencing. So I asked a class of 31 students that question. I'm going to show you their responses in just a moment. But as I said, this unit of study is a lot of vocabulary, a lot of semantics and jargon. So you're going to want to pause the video periodically and jot down some of this language that I share with you. So my asking students that question, how many hours of screen time uh, are you exposed to daily, is an example of, once I collect that data, of univariate data. Univariate meaning, if you look at the prefix, one variable. So we're going to look at different websites as reference points, but the example that's given here is that we weigh puppies and they have a particular weight. So that's the one variable that we've collected here. Not all data is univariate, as you might have guessed. Some data, for instance, is bivariate, and here's an example of some bivariate data. Particular company has ice cream sales and they track those ice cream sales versus the temperature on that particular day. So they are kind of keeping track and marking two sets of data at the same time. What were the sales and what was the temperature? So by contrast, what I asked my students was not bivariate, it was simply univariate data. Again, what is the number of hours of screen time that you think you're being exposed to daily? And once you've collected a set of univariate data, you want to generally be able to express it in some way. So what are some of the ways to express it? Well, one really kind of traditional way to express univariate data is to use a bar graph. You've probably done this in both elementary and middle school, um, but may not have thought deeply about what a bar graph shows. So here, for instance, someone asked a bunch of people, what's your favorite genre of movie, type of movie, and they fall into these 5 categories. And you can see that in this bar graph, each of the bars represents a different genre or category. So we generally say that bar graphs are a way to communicate categorical data. Four people liked comedies, or that's their favorite type of movie. By contrast, 5 people like action movies, and so on. So each of these is a separate category. And when we look at this bar graph, we can very quickly tell that the most popular category was romance, and the least popular category, at least in this data set, was drama. So that's how a bar graph would be used. By contrast, we could use what's called a histogram. And right away, you'll probably just, without even reading any definitions, see that something has changed. There are no longer categories here. There's no words here saying that there are different bins. What's happening is there's some continuity. So in fact, histograms tend to be used to show continuous data or quantitative data, data that we can kind of count. And have a look at the example that they provide us. They say that you measure the height of every orange tree in an orchard, and so those heights fall into a range of 100 centimeters all the way to 340 centimeters. And so you decide to kind of create these bins, for instance, from 100 to 150, 150 to 200. So every 50 centimeters, and then you drop into each of these bins the number of trees that fit into that particular height. So the histogram does not have categories. This is kind of numerical data here. and it's continuous. There is no break between each of these columns. So just to be clear here, you cannot refer to this as a bar graph, just as with the previous pictures that I shared with you here, you cannot refer to this as a histogram. They are separate entities altogether. So those are two ways that we can show and share univariate data. And then going back to the example that I give where I said that I surveyed my classes and asked them how many hours of screen time they were basically being exposed to daily, here are two more ways to represent data. This is called a dot plot. Generally, dots are used. I've used X's, which is fine. They're kind of interchangeable. And even though it appears that there's two variables here, there really are not. I didn't have to put this label here. All I'm keeping track of is uh, the number of hours each student is exposed to the screen. So, for instance, I've got two students here, these two X's, who each said that they got about an hour of screen time per day. I've got four students who said they get about 2 hours of screen time per day. So I think based on that, you can kind of read the rest. You'll notice that no students felt that they had 8 hours. And then these two students were kind of peculiar because they were claiming to have 9 hours of screen time per day. Now, screen time includes everything from your phone to a computer screen to a television screen. So that very well have been true that they had this number of hours. So you've got bar graphs, you've got histograms, you've got a dot plot. And by the way, there are 31 dots or X's here representing the 31 students in my class. And as the days go on, we'll talk about the shape of this data because it probably stands out to you that it has a bit of a pyramidal or bell shape to it, and that these two values are kind of off to the side. So we'll come up with language to describe the shape of this data and what we would describe these two data points as. But I wanted to kind of end this particular video by also suggesting that there's a fourth way to share univariate data, and that's a box and whisker plot. And you have to kind of look closely here to see that so-called box, this rectangle here. And then each of these lines, which terminates in this kind of vertical line, is a whisker. So there's a whisker here and a whisker here, and this is the box part. So we call this a box and whisker plot. And what I've done is actually list the numbers out in order from least to greatest. So again, here are my two students who said they had an hour's worth of screen time. Here I've got four students who said they had 2 hours and so on. And in future videos and future lessons, we'll talk about what all these labels mean. For now, let me kind of share with you that what I've done is find the median of this data set. Because there were 31 values, that's an odd number, so 15 and 15 would give me 30. This is the 31st value here. So there's 15 numbers to the left of this 4, 15 to the right of it. This would be the 31st number. So this is the median of the entire data set. And then if you just look at this half, this value, which we call Q1, quartile 1, is the median of the first half of the data set. And this value, which we call Q3, is the median of the second half of the data set. So this word that I keep on repeating, this word quartile, uh, I think that you can kind of guess that it means fourths. And so by using these three labels, Q1, Q2 here at the true median, and Q3, I've taken this data set and I've broken it up into four pieces. And the purpose behind that is so that you can focus on this middle piece, this middle 50% of the data, which is where most of the data, well, let me take that back, where the most relevant data is kind of contained. And if we want to talk about what most people are getting, by and large, how many hours of screen time are they getting, we're going to tend to look in this 50% as opposed to this first quartile or this last quartile. So we'll pick it up from there on our next video.